So we'll start by a review of our last lecture. So in the last lecture, basically what we successfully did is that we derived the diffusion equation. And we also put another constraint about the diffusion equation that we are studying the locally conserved particles, or like you know, like the particle number are conserved, so the particle can move from one spot to the other, but it cannot disappear. Okay. And then in the last lecture, we basically try to solve this equation. And at first, basically, we start from the no external force case, and basically we start with some kind of density profile. And at the beginning, we have some profile that at t equal to 0. Maybe you will have some profile that looks very in various different way. So with different initial condition, we want to understand how this density profile evolve as a function of time. But before we did that, we basically try to ask the first level question: if the system can reach equilibrium, that is, if there's the chance that this term is equal to 0, then we are able to solve the equilibrium configuration for our density profile. And in the case for no external force, what we found is that no matter what kind of initial density profile you start with, eventually you'll get an equilibrium configuration that is basically a homogeneous distribution of your density profile. Okay, so that's intuitively clear that if you have some particles in your room, and in the room you just basically release it, and then those particles will bounce back and forth, and eventually at the long time limit, they will basically spread out evenly in the room. Okay. So we also consider the case where if our system has some kind of external force, then we basically ask the same question, like how the density profile evolve as a function of time. But this time with the influence of the external force. And we solve this equation with certain boundary condition. And we found that under the suitable boundary condition, we'll find the equilibrium configuration to be a profile that have the exponential decay behavior. Okay, so here we are talking about specifically when the external force is basically the gravity force. Okay, so we also know what happened when we have external force at the equilibrium configuration. Basically, we just got an exponentially decay profile of our density. And then, so we almost understand what is the diffusion equation doing. So the last unanswered question is what happened during the in the middle, like as the time is evolving, but it is not infinite. Like the question is almost like asking, if I start from some kind of density profile and I evolve the density profile according to the diffusion equation, how this density profile will change as a function of time. Okay, so that's the question we posted. And in our last lecture, we discussed two methods. One is about the Fourier method. And at the end of the lecture, I mentioned something related to the Green's function. So today I'm going to review how we use these two methods to solve our diffusion equation again. Okay. So one of the key ingredients or the key idea is that the diffusion equation is a linear equation. What that means is that if rho 1 and rho 2 are both solutions to the diffusion equation, then the linear combination of it will also be a solution. Okay, that's one important observation. And the second important observation is that the diffusion equation is translational invariant. Okay. So now I'm in our last lecture, I kind of give you more like a hand-waving argument saying that you can just use Fourier transform and decompose your density profile in different wave vectors, and then solve that, and then you are able to use the Fourier method to solve your the diffusion equation. So here I'm going to give you another line of thoughts about like the idea is try to think from the point of view how translation symmetry enters the analysis of the diffusion equation. So that's the reason. Let's try to pose another question. Okay, the question we try to ask: why Fourier method? So Fourier method usually is useful when we are trying to study something with a translational symmetry. And usually when we talk about translational symmetry, we talk about translational symmetry in space. But also we can discuss the translational symmetry in time. But in this course, for the diffusion equation, we are not going to discuss this part yet, but we'll focus on the behavior of the translational symmetry in space. Okay. So let's try to make our problem more precise by formulating some of the operators related to the translational symmetry. So let's define translational symmetry operator. To be T delta. Okay. So it just means that you shift your system by an amount of delta. Then we can write down almost like the definition of the translation operator and the time evolved density profile. So let's try to write down what I meant. Okay. So here we define the translational symmetry operator to be T delta. And when we try to apply this translational operator to the evolved density profile, what does that mean? It just means that we are trying to apply the translational operator to a density profile. Oops, there's a typo here. It should be t equal to 0. Like initially, we start from some profile at t equal to 0, and the effect of this ut is basically the operator that evolved this particular density profile at t equal to 0 to some specific time t. Okay, so so this line is just very simple mathematical way to describe what we are doing when we try to apply the translational operator to a density profile at some time t. Okay, so this is okay. And here there's a parameter k. At this moment, we don't know what that is yet, but we'll just keep it there, and later you will become apparent what that means. Okay, but basically here, the only new thing that we introduce is this ut. It is just defining how the profile evolve as a function of time in an abstract way. Okay. So here we are going to try to think a little bit deeper about what do we mean by translational symmetry for our system. Okay. So I'm trying to write down the expression first, then I'll explain what that means. Okay. So at the left-hand side of the equation, basically, this is okay. Hope nothing is about to broke. But anyway, so the left-hand side of the equation, if you just look at the mathematical expression, first we have some kind of density profile, rho k of x at t equal to 0. Then we apply the time evolution operator ut on it. Okay. Then after that, we apply the translational symmetry operator on that. Okay. So that's why at the left-hand side, if you try to describe it in words, it is a translated time evolved density profile. Okay. And at the right-hand side, basically, we can also try to write down what does that mean. It is basically so basically it is a time evolved translated density profile. So instead, what we are doing is instead of like doing what we did previously, we take a density profile, and what we did is that we shift it to somewhere with a distance delta. And after we shift our initial profile to somewhere, we evolve it using this evolution operator ut. Okay. And the fact that these two are equivalent is basically a property that our system is translationally invariant. So you can evolve your density profile somewhere here, and it should be equivalent to, start from this initial configuration, and you should shift it to somewhere else, and then release it and let it evolve. So those two things are equivalent. That's basically from the fact that our system is translationally invariant. Okay, so this is basically the condition. Translation symmetry. Okay. So next, I'm going to explain a little bit about why we mentioned K. So when we try to apply the translation operator to this density profile labeled by K, okay, what we have in mind is that actually this translation operator is doing something to our density profile, but we want to convert it into some kind of eigenvalue or eigensystem problem. Okay, so in the most general case, this translation operator actually should be represented by some kind of big matrix. So that's why, in general, if you want to understand the effect of this operator, it is actually not so trivial. However, if you are able to find the eigenvector or the eigensystem of your translational operator, then using this basically definition of eigenvalue or eigenvector, then you can replace the operator T delta and replace its effect by a simple number lambda k, which is the eigenvalue. So that simplifies your analysis. Okay. So the next question is, okay, so this k, as we know, if we write it in this way, is basically a label for your eigenvalue of the translation operator. Okay. So the next step is like, combining this A, B, and C. Why the Fourier method is going to be a useful method for our analysis. So let's see. So let me just try to write down the line of argument. At this point, we'll just hold for a second about how to derive this lambda k. We'll just assume that we can derive it. And let's see if we can derive it, what kind of benefits we can get from there. So in the most general case, or like this is basically the definition. Let me just write it down. This is like nothing special. The first line is just the definition of the evolution operator. And the second line is basically we have the translation symmetry. And the next line is if we know the eigensystem. Of the translational operator. So usually, if we know the eigensystem of our translational operator, then this lambda k will just be a pure number. Then we can take it out easily. And this is basically lambda k times the time evolved density profile rho k of xt. So basically, what we observe here is that once we figure out what is k, then under the time evolution, actually this k is invariant during the process. Okay. So that means that if this k is a good number to characterize your density profile at first, then after some time of the evolution operation, then this density profile will be a time-dependent profile. But this k will still be a good label for each component. So that's what this derivation is telling us. So that's why it is going to be a useful idea to simplify our analysis if we know what is the eigensystem of translation operator T delta. Okay. So let's try to get back to the equation that we posted previously. That's basically this equation. Okay. So this is the eigenvalue or eigensystem equation for the translation operator. But we also know what translational operator is doing to a function because it just shifts the function to some to the positive direction by some amount of delta. So we also know this thing needs to be equal to this, right? So the question is, can we solve lambda k by this relation? Okay. And there are two ways to do that. One is basically you just stare at it and you found that there's a simple solution. And the corresponding lambda k is just exponential minus ik delta. Okay, you can just plug that in and then you'll see that's the solution. That's one way of doing things. Just, see this answer directly. And there's a more, more, to some extent, more strict way or to a more systematic way actually related to group theory. I'm not going to say too much about that, but I'll just post the keywords. So if you are interested, you can look it up. So the operator that we are dealing with is the translational operator, which means that you just shift your coordinate 1 unit. And that operation actually commute with each other, which means that the order of these operations doesn't matter. You can shift by delta 1 and then shift by delta 2. And eventually you got the answer, you shift delta 1 plus delta 2. And this result is identical with you shift delta 2 first and then shift delta 1. Okay. So that's a signature for the fact that translation symmetry form a group that is abelian. So and there's an important theorem about the property of abelian group is that you can represent group element by a one-dimensional irreducible representation. Or like the representation is always one-dimensional irreducible representation. Okay. And if you try to think of your system that's living on some kind of ring that has some periodic boundary condition, that's like after you move n step, you get back to itself. That means that this thing to the power of n needs to be identity. Okay. And if you represent this operator, translation operator, by a complex number, z, then it corresponds to the fact that z to the power of n needs to be 1. Okay. And usually you think of z as some kind of, complex number. So let's see. So the solution of this thing should be something like that if you just look at it. Okay. And here m goes from 1 to n. Okay. And if you stare at it for a while, you'll see that it looks like something like exponential ikx that we have learned, but just in a finite and discrete system. But you don't really need to worry about the discreteness of this group because, you can always try to go to the continuum limit for this group because it's a relatively simple group. But anyway, the point is that's why we have usually when you try to deal with particle in the box in the periodic boundary condition, you will usually have this k equal to 2 pi divided by L. Okay, that's like more from the group theory point of view. Okay, so at least I think we've tried to elaborate why Fourier method is going to be useful, because it basically attacks the property that the system is translational invariant. So once you decompose it into different component k, when you evolve the system, those k's will not mix with each other because of the derivation we just derived here. Okay. So I think that's something that I didn't really explain very well in the last lecture. So I hope that clarifies something like why we do it using this method. So are there any questions so far? Yes? Oh, gotcha. Yeah, I can remove that. That's for sure. Okay, so I think with this reasoning at the back of our mind, let's try to write down what we have tried to do in the Fourier method. Okay, so we said that we start from some density profile, and we can try to express it using this label of our eigenstates of the translation symmetry operator. Okay. So as I mentioned, the advantage is that these row k's will not mix with each other for our system. So because of that, we can just try to focus on if we try to plug that equation into our diffusion equation and see what will happen. Okay, and it turns out that if you do it term by term, then what you derive is that the target that you need to solve is this equation. Okay. You can just bravely plug this expression into the diffusion equation, then that's what you are going to get. Then you just do the derivation. And you can drop these exponential factors. And as we have demonstrated in the last lecture, that this thing is basically solved by this equation. Okay. Then once we know that, then the evolution is just I think I missed something. There should be T. Yeah. Okay. So so that's good. Basically, we solve our evolution operator using the Fourier method. And here, the only thing that we need to figure out is like, what is this object? And this object is basically simple because it's just the component of the Fourier transform at t equal to 0. And you can evaluate it by doing the integral. Okay. So of course, this thing have a continuous version. Let's try to write it down. So continuous limit of this expression. Nice. Okay. So at this moment, we want to ask what we can learn from here. So the first thing is that I'll just use number. This K actually is something related to the wavelength of the wave vector K. So we see that there's a exponential factor here. Here, okay. So when the wavelength is short, or when this K is large, that means that this component will be strongly suppressed as the time is evolving. Okay. So when K is relatively small, when you go to the long time limit, actually there's a better chance that you will survive because of this exponential suppressing factor. And another thing that we can learn is that in order to understand how this density profile evolve, we need to do an integral to evaluate rho K tilde. Okay. So for different density profile, if you give me density profile 1, I need to do the integral once. If you give me density profile 2, I need to do the integral twice. So basically, that's the process if you want to know how this density profile evolve as a function of time, because we need this rho k tilde at t equal to 0 as our input information. Then once we know rho k tilde, then the solution for this thing is basically, again, we construct each component k by summing all of them together, and then we got our final solution. Okay. And the combine them all together means integral over k. Okay, so that's basically the whole process to reconstruct the solution. Okay, so we can ask a question: are there some other ways that can, or like solve our problem in a more efficient way? And then that's the second method. That is basically the Green's function method. And I'll try to compare that with our previous method, such that you know like why we need to learn that. So the idea of Green's function method is useful is because it is basically based on one expression. Okay, so this is the identity or the definition of a Dirac delta function. So if I try to draw it, basically what that means is that I have some f of x. Basically, it is equivalent to wait a second. It's the advantage of using an electric board. I can think of it as some kind of combination of bunch of delta function, but with a proper weight related to the function f of x. Okay. So if we know this thing exists, like we can decompose the arbitrary function using the delta function, then maybe we can try to think in another way. If we have this expression, and if we know how a delta function evolves as a function of time under the diffusion equation, then it will be very useful for us to understand the physics behind. Okay, so we try to ask another question. Okay, and so basically that's to some extent the general definition, like what is a Green's function, because even though in our case we are going to solve it for diffusion equation, but in principle it can be worked with other kind of differential equations. Okay, like Schrodinger equation, you can also apply that. Okay, so let's try to write now the definition. So it's defined u of xt. Okay, so to some extent, it is a time evolution for a very special initial condition. Like the initial condition, now we set it to be the delta function. Okay, so now we are able to use the Fourier method again, and you'll see why it is a general approach. So let's try to write it more specifically. That's a special initial condition, and we want to solve okay. And then we can use the Fourier method again. So how to derive the solution? Basically, we need to find GK tilde at t equal to 0. And according to our previous derivation, we need to take the Fourier transform of our initial profile. But now this initial profile is a delta function. Okay, so this integral is almost trivial. So it just means that the system basically has a value only at x equal to 0. And for this function, when x equal to 0 is just 1. Okay. So once we know what G tilde k is, we can construct the solution according to our previous Fourier method by putting all these different components of k together. Wait, did I make some mistake? Yeah, I think I have a typo here, but it doesn't influence the result. Okay, and from this line, we know this quantity is just 1. Okay. So eventually, what we are doing is actually a Fourier transform or inverse Fourier transform of a Gaussian wave function, or a Gaussian function, sorry. And this thing will leave as an exercise for you in the homework, but all you need to do is just try to do the integral, and you'll find that this thing looks like this. So oops. So this is the Green's function of the diffusion equation. Okay. So wait. So somebody said that the screen is still at the almost blank notebook. I think that must be an internet problem or something. So please reconnect if you did not see anything, because I think I've already write a lot of things. So okay. So are there questions so far about the Green's function method? Okay. So if not, let's try to see how this Green's function method works. Yeah, please. No, I don't think it needs to be linear. The problem is that if it is nonlinear, usually you don't have a nice expression because you don't know how to solve it. But it exists. But the problem is you usually need to spend a lot of effort to really get it if you are able to get it. Yeah. But for linear equation, it is especially useful to demonstrate it because it is easy to derive it. Yeah. Okay, good. Okay, so let's try to take a look about how this thing is going to help us to understand the evolution of a arbitrary density profile. Because remember that oops, time is up. So basically, this is how basically that's the definition of the evolution of your density profile under the knowledge of what is your Green's function. Okay, so at t equal to 0, we know that okay, so let's try to write it more specifically. But I think maybe I'll stop here and I'll try to continue the writing in the next lecture, and maybe we'll take a 10-minute break. And if you have questions, just let me know. Okay, so hi everyone. So I think I'll continue our discussion. So let's see. So, no, why? Okay, so what I'm writing now is just the general expression for the evolved density profile. We can try to take a look at the limit case. At t equal to 0, what is our density profile? And you'll find that at t equal to 0, as the Green's function's boundary condition tells us that it needs to be a delta function. So eventually we got the initial condition that we plug it in. Okay, so this is just a self-consistent check that this expression is not nonsense. So we just show that at least at the initial condition case, it works. So so now, as we already know what is the solution of our Green's function, that's basically what we derived in this red box. So now we have a very general expression for the evolution of our density profile. It is basically the density profile at t equal to 0, and you make a you just do the integration. This is our Green's function. Oops, sorry. I think I need to replace that with x minus y. Okay. And dy. So that's our solution. So what it means is actually, if you start with some kind of initial condition, rho y at t equal to 0, say this is y. Okay. And basically, initially we think of it as a bunch of delta function. And the Green's function tells us like how this delta function evolves. And the statement is that then this wave function will evolve into some other form. But now, because we can keep track of how each one delta function evolve using this Green's function solution, then eventually we'll get our general solution. Okay. So So that's basically the diffusion equation and its final solution. So now we are trying to say like why we talk about this diffusion equation, which is a macroscopic equation. Now we are trying to make some connection with our microscopic understanding. So previously we said that for an n-step random walk, with step size A, we have derived the root mean square to be square root of n times the step size A. So that's the result we got previously. So the Green's function for the diffusion equation is basically a Gaussian wave function. That's basically this expression in the red box is basically a Gaussian function. And for the Gaussian function, we can try to calculate the standard deviation. So it's basically this square root of 2 dt. Okay. And in our microscopic derivation, we can identify the diffusion coefficient as a squared divided by 2 delta t. Okay, and a is like the deviation of the distribution function. So if you plug that expression into the standard deviation of the Gaussian function, what we will see is that this thing is basically 2 times a squared divided by 2 delta t times t. Okay, so we just finished this simple algebra. What we found is that this thing is square root of t divided by delta t times a. Okay, and t divided by delta t basically is like, you know, how many steps have been performed in this macroscopic process. Okay, so this thing is basically square root n times a. Okay, so we see that actually, you know, after a long journey, that initially we start from the random walk, that we assume that the step size is unit is of unit length. Okay, and it is fixed step size. And then we do it in 1D and 2D, and we found that we can derive the expression of this, the variance of the random walk to be have this square root n behavior. Exactly, there's no approximation, and you don't need a large n or something. You just do it. But here we are trying to get a little bit further about our understanding by assuming that the microscopic process might not be perfect. Now the random walk can take a random step size. It could be, you know, sometimes it make a bigger move and sometimes it just move nearby its origin. So once we relax that, then we also try to form a macroscopic expression of this kind of microscopic model. And what we found is that actually the macroscopic theory also suggests that the variance will also be proportional with square root of n. Okay, so that also means that the step size, even though at first it seems like it is important for our derivation, actually it's not really an important factor for our square root n behavior. So this is another example that some of the detail of our microscopic model is not really important, and that leads to the same universal behavior of the square root n behavior. So that's like the universality class idea again, but now in a more detoured way. Okay, so that's one thing, and the other thing is that let me try to write down the Green's function again. To some extent, this expression for the Green's function is directly related to the central limit theorem. And it just says that the sum of independent random variables. The sum of independent random variables has a probability distribution that converges to a Gaussian. Okay, so so you will be proud of your homework that you will show this result, and this is a quite remarkable result. So so let's try to think a little bit about what we have done. So we said that we start from some initial density profile, and we assume the dynamics is governed by random walks. So we derive the diffusion equation. So we know how this density profile evolves as a function of time. And eventually it reaches the equilibrium configuration that we know basically is either uniform distribution or exponential decay profile when there's external field. So basically, we just described a very simple example of how a system evolved into an equilibrium state. Okay, but I need to say that this is a relatively simple model such that we can keep track of what happened in the middle. However, this problem is actually a quite open question. In the classical system, it could relate it to some highly nonlinear physics, for example, chaotic physics. They actually plays quite important role to understand how a classical system start from some closed classical system starts from some configuration and how it reaches its equilibrium configuration. Okay, so it is not fully understood in the sense that we have a general description about that. And for the quantum system, it is also not known. That question, like how a closed quantum system starting from some initial configuration and eventually it reaches some kind of equilibrium phase, is also an open question. Especially, it is related to one of the recent research topic, which is called many-body localization. It kind of asks the question, if you start from a closed quantum system, will it reach its thermal equilibrium, which means that will the system eventually be described by some kind of thermal ensemble? Okay, and the answer is sometimes it is no. So eventually the many-body wave function will stop themselves such that they refuse to be described by some kind of statistical thermal ensemble. Okay, so that's some discovery just nearby, I don't know, 2010. Like now it's like 10 years ago, but from the scale of physics, it's quite recent. So, so I think I'll stop here and then enter our next section about some basic understanding about statistics.